Well, let's see. We were starting to talk about probability. And so far we had calculated probability for a single event. So what we're building up to in the next couple of sections is how we could find maybe a probability for two things at the same time. Like we'll see here probability of like one event and another occurring. Or when we move on to 3.3, the probability of one event or another occurring. So building on our probability idea. To get started on the and, we need to know what independent and dependent events are. Let me give you a minute to check out the definitions, and then we'll talk them over together. So they probably mean kind of what you would expect. We say two things are independent if they're completely separate. There's no kind of a link between them affecting probabilities. Probability, by the way, is a key part of the definition, but it's easy to kind of overlook or forget. We are talking about some kind of like a probability link, meaning if one of the events happens, does it affect or change the probability of the other one happening? If it doesn't, if they're completely separate, no probability link, that's what we mean by independent events. If we know our events are independent, we can treat them certain ways, knowing there's no link. On the other hand, if one of them occurring does affect the chances or probability of the other one occurring, that's what we mean by dependent. So there is something kind of linking them together. Each one affects the probability of the other somehow. We're going to practice a little bit first, just deciding if events are independent or dependent by tossing a coin and picking a card from the deck. So let's say you did toss the coin, you got heads or tails. Does that affect the probability of what you pick out of the deck? No, so these would be independent. You got it. Totally separate things, no link between the coin toss and the card that we're picking. Number 2 says we've got a drawer full of socks. Currently, we're going to take one out. We're not going to replace it, and then we're going to go and take a second sock out of the drawer. So the two parts are taking out the first sock and then taking out the second sock. So let's see, maybe there are 10 socks in the drawer. When we go to pick the first sock, our probabilities would be out of 10, right? 10 socks in the drawer. So we take one out, we keep it out, and then go back to select the second sock. Are the probabilities still out of 10? They're out of 9 now, right? So keeping that sock out changes the probabilities, making these dependent. That's right. This third one sometimes gets a bit of discussion going. People aren't sure how they feel about it. But here's where, again, it's important to remember, we're just saying some kind of a probability link. We're not saying if you get a raise, you're definitely going to go buy a car. We're just asking, do you think getting a raise would change the chance that you'd go out and buy something like a car? Yeah, there's a bit of a link there. Not getting a raise would maybe mean not buying the car. People tend to agree that those are also dependent. And again, remember, we're not saying that's definitely going to happen, just that there is some kind of a link. Having more money means you might buy something you've been needing to buy. See anything you'd like to double check so far about examples 1, 2, or 3? I've got a 3 for you to try down at the bottom of the page. Your turn to give it a go. I see anything you'd like to double check on our discussion so far? Or need a little help get started on these 3? Just let me know. like a little longer to think before we check them out. Are you deciding on more dependent or more independent answers? Dependent. Which ones are you thinking are dependent? Number 1 and 2? Well, let's check it out. The color of a father's eyes does affect the color of the daughter's eyes, doesn't it? There's a link there. Probability link. If you don't pay your parking meter, you're more likely to get a ticket. There's a probability link there as well. Sounding good? And that would leave us with independent for number 3. Ball is selected from a bin. Replaced, second ball is selected. Why is this one different from the socks? We said the socks was dependent.
Put the ball back.
This time they are putting the first one back before they pick the second one. Yeah, so you're back to the original total. Probabilities would stay the same. Sounds like a good start. Anything you want to double check about our definitions so far? Well, one other definition we need before we get into these probabilities all the way is called a conditional probability. Let me give you a minute to see what we know about it. Try not to let the A's and the B's worry you too much. They're just trying to label the two items, the two events. So this name, conditional probability, is kind of related to the idea of if there's a condition on something, it sort of means, something else needs to happen before this is going to happen. Conditional probability also takes into account that something else has already happened. So if we start finding the probability of something based on the idea that something else has already happened, we call that a conditional probability. We want to know what the probability of B is on the condition or knowing that A has already occurred. The way we would read this notation right here is kind of directly from all the symbols. We got P for probability. The parenthesis is read of. So the probability of B, the vertical line there is read given that. And then after the vertical line, we see A. So this is the notation for finding the probability of B given A. Like, what are the chances of B happening if we already know that A has happened? Well, that's something we need to think about when the events are dependent. You might see right below that, we've got two versions of something called the multiplication rule. One version is for events that are dependent, and that's when this conditional probability shows up. The other version is for events that are independent, so no conditional probability. Remember we said if they're dependent, there is some kind of a link and it's going to affect the probability. So we would need to take that into account, think about it, if we're going to find probabilities for dependent events. Well, let's see what they have in common. These multiplication rules are both for finding the probability of two things occurring, like event A and event B both occurring. So exactly the same as far as what they're finding. If we have independent events that are completely separate, it is as simple as just multiplying the two individual probabilities. So whatever the probability of A is times whatever the probability of B is. We'll see, by the way, you might have already seen in other math classes that the word and typically helps us know we need to multiply. So that's why it's called the multiplication rule, because we're multiplying those two probabilities. When they're independent, separate, so pretty straightforward. If A and B are dependent though, we need to take that into account. And still we can start with the probability of A times. And we can kind of finish off with the probability of B, but if they are dependent, we need to take into account that A has already happened when we crunch the numbers here. Got our first example of a multiplication rule down at the bottom of the page. So we'll give it a go, try it out in just a sec. Anything you want to double check so far about conditional or multiplication rules? Well, let me give you a minute to read through the example, see what we know and what they're asking us to figure out. Like a pretty big flashlight, doesn't it, with 6 batteries? Picturing big flashlight batteries, maybe they're smaller. So in this flashlight, we have 6 batteries and 3 of them are defective. So I'm just kind of getting my information together here. I'm thinking 6 batteries, 3 of them are defective. If we're going to pick 2 at random without replacement, we want to find the probability that both of the batteries we pick are defective. So without replacement, in other words, we'll pick out one of the batteries and we don't put it back, we keep it out. And then we pick the second one, so we'll end up with 2. Probability they're both defective. Does it sound like the way we're selecting them here would be independent or dependent? We've got 6 batteries, we pick one out, we go back and we pick another one. Are the probabilities different the second time? Yeah, so that would be dependent, wouldn't it? Dependent situation. So we're going to need our version of the multiplication rule that says probability of A and B equals probability of A times probability of B given A. The one for dependent, where that conditional probability is involved. Well, they said to find the probability that both of the batteries we pick are defective. So I'm going to start with a little bit of labeling. I'm finding a probability, and in the parentheses, I'll describe the event. It doesn't seem to match exactly A and B the way they've stated it. Do you think there's any way to think about both of them being defective that would use the word and? Both of them are defective. What does that mean? That means the first one is and the second one is both defective. First one and second one. That will kind of help us know what's the A and what's the B in our formula. So the first one being defective, that could be the A in the formula. And the second one being defective, that could be the B. Like some of our tree diagrams the other day, want to break it down into a sequence, figure out what's first, that'd be the A, and what's second, that would be the B. So in terms of the notation in the formula, that means for probability of A, in this case, we want to find the probability that the first one is defective. And then we're going to multiply that by probability of B given A. In this case, probability of B is the probability that the second one we pick is defective. Given that A occurred, and A was that the first one was defective. In the end, we're trying to find the 2 probabilities to multiply together. lots of extra notes and labeling on our very first example. I was taking notes, I just write all that down, so when I look back at it, I have an idea where all these numbers came from in a minute. So that's the plan. Matching up our situation here with the formulas we have to use. Let's put in some numbers. If we've got those 6 batteries and 3 of them are defective, what's the probability that the first one we pick is defective? What'd you say? 50%, yeah, 3 out of 6.5, 1/2, any of those would be fine. And now for our second probability, let's assume the first one we picked was defective. And remember, they say we're not going to replace it, so we're taking out one of the defective batteries. What's the probability now when we go back that we pick another defective one? 2 out of 5. Yeah, the numbers have changed because it's dependent, like we expected. Taking that first battery affects the probability of the second choice. So we just need to figure out what 1/2 or 3/6 times 2/5 is. How about we try giving the answer as a decimal and a fraction for practice? So I'm just going to type that whole 3/6 times 2/5 in at once. If my calculator will let me. It's not happy. Let's try this again. Or I could do it with parentheses.
So for the 2/5 one, is it because we have to assume that the first one we did pick a defective one?
That's right. Yeah. Then because it says B given A, so whatever A was, we need to assume that did happen.
Okay.
When we find the next probability. Looks like 0.2 as a decimal. Does that part sound okay? And I think we mentioned the other day how to turn that back into a fraction. Do you guys remember? Math. The very first one with the arrow and the frac turns it back into a fraction. 1/5. So 0.2 or 1/5 would be the probability we get 2 defective batteries. I know the notation and the formula make it seem kind of more complicated than it is. In the end, we're just multiplying 2 numbers, but the notation and the formula do help us figure out what those 2 numbers should be. Here's our first example of a multiplication rule for dependent events. How about some questions for us so far? Well, gotta ask another question where we need a multiplication rule over on the next page. Give you a minute to read it over. Remember, one of the first things we need to do is decide if it's dependent or independent, so we know which version of the rule to use. They don't seem to mention if there's replacement or not. So we'll probably have to read between the lines a little bit. Dig in our brains back to chapter 1, maybe. Guys, I happen to remember when we were like randomly selecting rectangles or randomly selecting baseball teams for practice back in chapter 1. If there was replacement, like if we picked a baseball team, does the name go back on the list so that it could be picked again? Remember, we had some duplicates. Plain old random selection is with replacement. So if they don't say anything else about it, they just say selected at random, we should assume there's replacement. So like if a name is picked off the list, it is replaced and stays on the list and could be picked again. What does that mean as far as dependent or independent then? Independent, that's right. So plain old random selection is always independent unless they tell us otherwise. that we're gonna have replacement? Or that we're not gonna have replacement? Well, that's probably gonna be a big help because we don't really have many numbers to work with. We've only got this 1%. So if the numbers were gonna change, if it was dependent, that would be tricky. Let me give you a minute to think how we might start with our multiplication rules now that we know it's independent. I think we'll have to extend our rule a little bit, won't we? Because it was for A and B, but now we're talking about three things. Since they are independent, we should be able to extend it. Let's say the probability of A and B and C would equal probability of A times probability of B times probability of C. Before we just had A and B. But since they're independent, we could have any number of things, just keep multiplying those probabilities. They're asking us if three are randomly selected, what's the probability all three are US citizens? So all three, again, doesn't appear to have the word and in it. Let's think about what that means. That means the first one is a US citizen, and the second one, and the third one. So that would be our A and our B and our C in the formula. We just want to find the probability of each of these things separately and multiply them together. So what do you think? If we had this list of all of the Major League Soccer players and we randomly selected one, what is the probability we pick a US citizen? We don't have many numbers to work with, do we? Think we could do anything with that 80.1? The percent, is there a way we could use it as a probability? 80.1 out of 100? Or in other words, 0.801? A percent's easily switched to a decimal. So 80%, meaning like 0.8 probability. So remember that name is replaced, goes back on the list. We have the same master list when we go to pick our second name. What would the probability be for a US citizen this time? The same, that's right. And a good thing too, because that's the only number we have. And then that again for the third one. That's right. So we're really just raising 801 to the third power when we multiply it by itself 3 times. We talked about exponents back when we first broke out the calculators. Anybody remember how we could raise this to the third power? Is that little rooftop caret symbol right above the division? Yeah. Some calculators have pretty print and make it look like an exponent. Others just show the rooftop and the 3. With probabilities, we're usually asked to round to 3 decimal places. So if we went 3 decimal places on this one, looking like 0.514, yeah. I know we wrote down a lot. When you get the hang of it, you probably just write down your numbers and find your answer. Maybe you do a little labeling at the beginning. But again, for our notes, for our first couple of examples, good to have lots of info. Yeah,
All like the questions worded like that, we do it the exact same.
we'll see several more, so you can see. So there's a little bit of a variation here and there, but largely, yeah.
Okay.
Knowing that the only number we had was that percent, there's a really good chance we're just gonna use that percent over and over and over, however many times, like 3 times for the 3 players. Anything else we wanna check on so far? This next example, number 1's real similar to some things we have already done, so why don't you jump in and see if you can get it figured out. If it needs rounding, 3 places would be a good number of decimals to go with again. My new will help finish up the last problem or get started on this.
So for the independent, like it depends how many, so how many apply, like if it was 3 or by 4, you
That'll
multiply.
tell you how many to multiply, yeah.
For dependent, is it always 2?
Yeah, for us, yes, because it gets too complicated if it's more than 2.
Okay.
Yeah.
Thanks.
Yeah, that's a good hint, right? If it's more than 2. Independent. This one also says selected at random, so we can assume independent. And very similar, we're looking for the probability that all 3 have assistantships this time. You guys know what an assistantship is for the graduate school? To help pay your way, like I had a teaching assistantship, so I taught classes and helped pay my tuition. There's research assistantships. Good way to help pay for graduate school, if you're going that direction. At any rate, all 3 means the first one and the second one and the third one, so we're multiplying 3 numbers together. What would be the probability that someone does have an assistantship if you pick their name randomly off the list? Based on 60%, 0.6 or 0.60. And it's independent. We're replacing the name, so the same over and over and over again. We could write it as 0.6 to the third. And what does it come out to be? 0.216. Nice. Anybody see anything they want to double check on that one? To answer parts 2 and 3, we need to remember a little bit about complements from last time. You might remember the complement was like the rest of the subset or the opposite. So in this case, we could say maybe, okay, if 60% of these students have assistantships, then what percent don't? 40. Yeah, what are we doing? We're just saying 60 out of 100 leaves 40. Yep, 100 minus 60. And that would help us find a probability we need for question 2. Now they want us to find a probability that none of the 3 have assistantships. Which would mean the first one doesn't, and the second one doesn't, and the third one doesn't. So the probability that they don't, we're seeing now is 0.4. So we want to multiply that by itself 3 times. There's an example where we can use the idea of complements to turn around the information and answer kind of the opposite question, like all 3 versus none. Those are the 2 extremes. That answer come out to be kind of high or kind of low for a probability. Yeah, remember what the range is? It can go anywhere from 0 up to 1. Yeah, so that one was quite low. I think it's interesting sometimes to see how much they change. Like, we started out by saying there's a 60% chance one person has an assistantship. But when we put 3 people in there, all of a sudden it's down to a 20. 0.2 is a lot lower. 40 is already kind of low. But when we say 3 people have to meet that criteria, it comes out super low. Number 3 also requires a little bit of the idea of complements. Anything we want to back up and double check about 2 before we see? So this time we want the probability that at least one of the 3 that are selected has an assistantship. At least one. So let's see. Let me a little room over here for some thinking. We're talking about 3 people total. That means that all 3 of them could have an assistantship, or just 2, or 1, or none. That's the only possibilities, right? If we're talking about a total of 3. Which of these would qualify for at least 1? 1 or higher? Yeah, so they basically want that combined probability. If we had more tools on our belt, we could potentially find each one separately and gather them all together. That turns out to be a little complicated, using some things we don't know yet. But if you think about it, we do already know this probability. We just found the probability for none. 0 of the 3 having an assistantship. It was 0.064. We saw last time if your entire sample space is represented, those probabilities should add up to, do you remember? 1? Yeah. Okay, well, I already know this number is 0.064. And I'm trying to find this combined total. Think we could kind of work around somehow to figure out the missing number? If we know they should all total 1, and we already know that part is 0.064, how can we figure what this part must be? 1 minus, yeah. 1 minus 0.064. And then it turns out that's always true. The probability of at least 1 is always 1 minus the probability of none. So that's a trick we'll be asked to use now and then. It goes back to the idea of complements because 1, 2, 3 is the rest or the complement of 0. So those 2 probabilities should add up to 1. .064 was a really small probability. When we subtract it from 1, we should get a really large probability. Like 0.936. Be a pretty handy trick. Usually comes up in a question where we've had multiple parts, and probably in one of the previous parts, we've already found the probability of none. So we can just subtract it from 1. That trick, by the way, wouldn't work for any other at least. Like if it said at least 2, we wouldn't be able to do the same thing, or at least 3. Just that 1 happens to work out so easily. So a couple of different twists and turns we might need to use with our multiplication rule and idea of complement. Anything you want to clear up about number 3 or number 2 or anything on this page? The next couple of pages are a few versions of homework problems that people have asked about at times. So if you're ready to jump on in, page 4, I think something strange will happen right there in part number 1. So maybe get started and let us know when you come up with something weird. Is something weird?
Yeah,
Yeah.
we get the E, you have to just move it over 4 places.
That's right.
Thanks.
Yeah. Are you already writing less and less on each one? Maybe a little bit of labeling, saying what we're finding. Maybe a little bit to show what you're multiplying. And then our answer. So we've got 4 unrelated people this time. Randomly selected, independent. What number should we multiply by itself 4 times? 0.12? Yeah. Based on that 12%. The chance that each person selected is B positive is going to be 0.12. And there's where something weird happens, right? Raising that to the 4th power or multiplying it 4 times. For starters, you might look and see that your answer is coming out to be 2 point something. And hopefully you think, oh, that's not right. Probability should never be bigger than 1. So that looks a little fishy. And then you keep looking and it gets even weirder because there's a letter in there. 2.0736 E negative 4. Anybody know what the calculator's trying to do there? Letting us know the decimal moves. It's their calculator's version of scientific notation. So 2.0736. That's the same as you might have seen written this way sometimes, times 10 to the negative 4th. That E replaces the times 10 in scientific notation. So that usually means we have a really big number or a really small number, and it's being abbreviated. The decimal is not really between the 2 and the 0. Where is it actually? It's actually 4 places to the left. Yeah, the 4 tells us how many places to move it, and whether it's positive or negative tells us whether to move it to the right or to the left. So the decimal is not really here. It's really 4 places to the left. Each of those new places gets filled in with a 0. And we'd probably be asked to round this one to 4 decimal places, which would make it 0.0002. Scientific notation. Good chance you've seen it before, may or may not have been very recently. And you may or may not have ever seen it on the calculator with the E like that. Number 2 has a little bit of a strange rounding to it, so we might want to give it a look also. Anybody need a little help on number 1, finishing it off first? A little more info about the scientific notation or anything? Here's where we need the idea of complements again. Like if 12% of people do have display type, what percent don't? Out of 100%, 12% do. So 88% don't? Yeah. So 0.88 would be the number we can use to answer this question. Most of the time, we're asked around the 3 decimal places. The previous one, we extended to 4s, so it wouldn't wipe out the number. Otherwise, it would have just been 0. So let's see if we can do 3 places on this one. That means we need to look at the 4th digit after the decimal. If it's 5 or higher, what's going to happen? That 6 is going to bump the 9 up to a 0, like 10, which carries over and bumps the other 9 up to 0, like 10, which carries over and bumps the 5 up to 6. So this turns out to be 0.6. If you want to kind of emphasize that you tried to round it to 3 places, you could throw on a few zeros. Now that we've got the probability of none, it'd be real easy to find a probability that at least one of the 4 has type B positive. Give you a chance to try to find that trick and use it again. Folks getting 0.4 also? What probability do you think an unusual event would have? Should it be high? Should it be low? Something's unusual. Not very likely. Probability would be low. Yeah. So what do we know about probability? Low means close to 0. Yeah. The official definition of an unusual event is one where the probability is less than 0.05. Which is like saying it has less than a 5% chance of happening. Unlikely. So we could look back through our answers and see if any of them happen to be less than 0.05. Not 0.5, but 0.05. Did any of them qualify? Let's see, number 1, the 0002 was definitely smaller, wasn't it? All those zeros make it tiny. How about number 2? Is 0.6 less than 0.05? 0.6 is like 60%. 0.5 is like, or 0.5 is like 5%. That one's too high to be unusual, isn't it? What about the 0.4? Is that one unusual? No, that's like 40%. So just one. Anything we want to double check there? I think we're ready to have a good time for our break. We'll get back to it in 10 minutes.
You can't do anything less the game, so I want to fantasy. Okay, that's not it's something. So my opponent had Geno Smith and I had DK. I needed DK to get a touchdown and Geno to do nothing else the rest of the game. I didn't work out as fairly. That's and he left the game. Drew Lock got a completion to DK, so I won by like 0.8 points. Hey.
Go ahead, starts to come back together. We've been looking mostly at independent questions lately. No, said it wrong. We've been looking mostly at dependent questions lately. And I want to see how maybe some of these same twists and turns can work on the other. I'll just quit trying to say which one. The other kind. So one more flip of the page there to page 5. Another question from homework that I tend to get asked about a good bit. Few minutes to read over the new scenario and see about starting on question number 1. A couple things are a little bit different about it. We don't have a percent this time. We've got some numbers to work with. 800 US adults, 205 think this way. With replacement, without replacement is also a little different, isn't it? Without replacement. So when one name is selected, it's kept off of the list. Not as many names to pick from the next time. Would that make this one independent or dependent? Dependent, yeah. So a couple of things make it a little different than the previous one. See if you could still find the probability they're looking for. Switching back to dependent, you might find the formula and notation a little helpful. More so than we have been using it lately. You're gonna need to make sure to take that conditional probability into account in our second probability. So we need to find the probability that the first one we pick thinks celebrities are good role models times. What should that condition be? Probability that the second one thinks that same way, given that the first one does. Yeah, it's gonna be a repeat of whatever was in this first set of parentheses. Yeah. Did you have something else, Jason? Or? So hopefully with the numbers they've given us, we can find those two probabilities, multiply them together. Should make a decimal. Let's stick with 3 decimal places. What can we use for that first probability? We've got an 800, we've got a 205. Couldn't we just say 205 out of 800?
Yeah.
Yeah. And now once that first name is picked, if we don't replace it, that means we have 1 fewer adults total, right? And the first one we picked does think that way, so we have 1 fewer people that think that way. So we're talking 204 out of 799 for our second probability. because we kept out a name and that name was someone who did think celebrities were good role models. Takes down the total, takes down the number who think that way. We can do something dependent when we have the raw numbers like this, because it's not a percent, we have the ability to take one off and bring it down a little bit. Anybody else getting 0.065? So the condition is that whatever that first probability was actually happened. So we think the first person we picked does think most celebrities are good role models. So we're keeping out that one person. Meaning now only 204 think that way, and there's only 799 total. Dependent, we said that means the probability is going to be affected and changed because we're keeping that name out. And what would you like to ask about number one? So now we're going to try sort of a complements question. Find the probability that neither adult thinks celebrities are good role models. Any idea how we could kind of turn our numbers around and talk about the probability someone doesn't agree with that? Yeah,
You do 800 minus 205.
You got it. yeah, 595. Yeah, so out of the 800, if 205 do think this way, that means 595 don't. So 595 out of the 800 don't think that way. That would help us with our first probability, wouldn't it? 595 out of 800. And now what about the second probability? If we're gonna take one name out, gonna assume that it was someone, that first one doesn't think this way. Should we still go with 595? No, it'd be down to 594. Yeah, out of 799. That's right. Good at making my calculator disappear, aren't I? Five, 3. Even if we've scared you off with these first two, if they were complicated at all, I might still try number 3 because it's still pretty straightforward. Back to the at least one probability. What are we seeing so far? We want to talk about a little bit more. Anything on part 2? Or we're back on part 1. Usually when they ask us at least one, we've already calculated the probability of none somewhere along the way. What? So the trick is to just subtract that probability of none from 1, like our previous answer subtracted from 1. 0.447. Anything we wanna check on that page before we see what's next? Pretty common for probability questions to ask about a deck of cards. And sometimes people know a deck of cards really well, other times they don't. So let's just kind of go over some of the basics, make sure we have a bit of information in case we need to know about a deck of cards. You might be able to jump right in and answer them all straight away. Got 6 questions down there. Give you a minute to see what you know already. Have you all ever played 52 card pickup? Why is it called 52 card pickup? Because there's 52 cards in a deck, right? How many suits are there? 4? Yeah, what do we mean by the suits? That's like the hearts, diamonds, spades, and clubs. Which of those suits are black? Spades and clubs, yep. And the hearts and diamonds are in red. So there's 52 cards altogether and 4 different suits. How many cards in each suit? 13? Yeah. How many red cards would there be? 26. And same for black cards, right? The deck is half red cards and half black cards. What do we mean by face cards? What would that include? That would include kings, queens, and jacks, yeah. Not aces. Sometimes people want to put aces in there. But just the ones that actually have faces on them, like a king has a face and a queen has a face. Jack has a face. So king, queen, jack in each of the suits. How many face cards altogether? 12. Nice. Anything we want to double check? On our next test's formula sheet, I'll put that little picture of the deck of cards on there in case that's not something you're so familiar with. There's a homework question about deck of cards where we need to use one of our multiplication rules here in 3.2. And it has something a little different in it than we've seen in any other problem so far. So let's try it next. Give you a minute to see what it's about and maybe get started, hopefully.
Which question is on homework?
At the bottom of this page.
Oh, I thought you were, my bad.
There it is, yeah. We'll need to decide if the situation is independent or dependent. And that'll help us know how to use our multiplication rule. What do they tell us that'll help us decide? As far as independent or dependent, what's the most important phrase in here? Not replace, yeah. So we're gonna keep it out, meaning we have less cards to choose from the next time. That makes it dependent. You got it. So we're gonna need to use that conditional probability to find the probability of a black card and then a red card. Looks like choosing a black card would be the A. Event A, choosing a red card would be the event B. So we'll start with the probability of choosing a black card. And multiply by the probability of choosing a red card. Assuming that the first card was black. Three decimal places would be a good rounding rule again. There's our plan. Now we just need to find the right numbers. Anybody want to check anything about our plan? Yes, I can nothing on the numbers. So when we pick that first card out of that standard deck, what's the probability we get a black card? How many black cards in the deck? Out of 52 total? Yeah. Now, assuming we did pick a black card and we kept it out of the deck, when we go back, what's the probability we then pick a red card? 26 out of 51. Yeah. So that's a little different than last time, right? Last time the top number went down one and so did the bottom number. But this time the top number didn't go down because we're talking about a different color. Assuming the first one was black, there's still 26 red cards. But we do have one less total number since we kept a card out. Looking like 0.255. When it's all multiplied and rounded. Anybody need a little help there? Let's peek into our 3.2 homework. Make sure we're feeling ready. You got the printout or laptop, whatever you prefer. And we'll give everything a little peek, make sure it looks familiar, and then start working a few problems. I need a little help finishing up anything in the notes. If you are looking at the paper version of the homework, number 17 didn't print out real well. There should be an equal sign between those two things. I'll write it on the screen in case you want to make a note on number 17. It should say probability of A given B equals probability of B. I find anything looks a little strange that we need to know about? Need to look up, yeah. So how many numbers in that jar? 318. Kind of like when we talk about rolling the die and you can roll and I need a little help with anything? Here, looking at the paper version, we've got some answers on the screen for page 1. The question I've been asked the most about so far today is number 11. If you want to check something to make sure it doesn't trip you up later, you might jump to number 11. Highest to lowest. Start with the highest and work your way down to the lowest. For 11 gives us a percent, and it also gives us some raw numbers. It's like we need to use both or all of them to get the question answered. Got the work and answer on the screen for number 11 on the printout.